Hi everyone, welcome back to Royan Study Corner. I am Royan, and in today's video, before I even say that, the aim here is to make learning as fun, easy, and as accessible as possible. So, the aim of today's video is to focus on forces. Now, we're used to forces. We've heard about forces our entire life. We know that a force is a push or a pull. Now we're just going to add on to that a little bit more, learn a little bit more about forces, and learn a calculation on how we can calculate a particular force. So let's get started. Now, if we're going to talk about forces, the first thing that we really need to talk about is what exactly is a force. Now, we've known a definition for most of our lives that a force is a push or a pull. And this is correct. But what we're going to do now is just add another definition to it that essentially means the same thing. So let's look at what it says. A force is any action which changes or tends to change the state of rest or constant state of motion of an object. So let's think about it. You're in PriceMart or any grocery for that matter, and you go to where they have the trolleys stacked out front. This trolley is stationary. It's not moving, so it is in a state of rest. You pull this trolley out from that. Now it's moving backwards towards you. So your action changed that trolley from being at rest to being in motion, which what you did there was you pulled the trolley. Now, once you pull it out from that stack of trolleys, you start pushing it towards the entrance. We hear that word pushing, which we know is a force. And if you think about it, all the time when you were pulling the trolley out, you were pulling it towards you. Now you're pushing it away from you towards the entrance. So you have just changed the constant state of motion that trolley was in. So we see it ties back into the same push or pull. Now, what are the things that a force can change? A force can change the size, shape, or motion of a body. So let's look at a few examples to see exactly how this happens. Here we see in the first picture, a man uses a force to move a stationary lawnmower. Now, if we think about it, he's pushing the lawnmower, so he's changing that motion. It was stationary, now it's moving. Remember, we said that the force can change size, shape, or motion. Now, the footballer uses a force to change the direction of motion of a ball, which is essentially still changing its motion, because maybe before its motion was heading east, and now because he kicked it, it's going to be heading west. A cyclist uses a bigger force to pedal his bike and increase its speed. So he's changing the motion of a body again. And finally, a baker uses a force on his dough to shape it into a curry puff. Now, if you think about it, he's changing the shape into making that pastry, and he's changing the size because he's going to cut it up, roll it into balls, whatever. So he is changing both the shape and size. So these are just a few of the scenarios, and there are scenarios all around us if you think about it, where any push or pull that you exert can change the size, shape, or motion of a body. Now, we've talked about what a force is and what are its effects. But the truth is there are lots of different forces, and we have to look at all of them. Now, these forces can be grouped into contact forces, and here we have distance, or what I prefer to say is non-contact forces. Now, their names are self-explanatory. Contact forces mean they have to be physically in contact for the force to exist. And distance forces, or as I prefer to say, non-contact forces, act at a distance. Now let's look at some examples of these forces. Now, This is a little reference sheet that I absolutely love, and I got it from Joshua Ellis on TPT, or Teachers Pay Teachers. Now, if you're an educator, sorry, you most likely will know about Teachers Pay Teachers. They have like tons of resources, because teachers can make stuff and post it there, so you can pay for it, or there are free resources. So this particular one is free, and I really like it because it's a concise explanation of all of the different types of forces. We see in the heading contact forces, a force that can only act when two objects are touching each other or in contact. We have a friction, we have a definition, and we have examples: air resistance, definition, examples, and we have that here for all of the different contact forces. Now, I'm not going to go through this in detail because I think his handout is really straightforward and really good. So what I'm going to do is I'll post a link in the description box, so you can click on that link and it will take you to Teachers Pay Teachers, where you can go and, well, you'll have to sign up first, and you can download this for free. So it is completely free, and then you could take this, keep it in your folder, stick it in your notebook, whatever you feel to do. Now, this is the second page of his handout, where he talks about contact forces, or sorry, non-contact forces. And it says that a force that acts between two objects that are not touching or not in contact are non-contact forces. And we have three examples here: gravitational, magnetic, and electrostatic. Now, I'm not going to go through all of these in detail, but because we're going to talk a little bit more about gravitational force a little bit further down in this video, I just want us to look at the definition. Now, gravitational force, the definition is a force that attracts any two objects with a mass. We see the two diagrams that he has is Earth and what I'm assuming is the moon, and we're seeing that force there, and apples and an apple falling down to the ground. Now, gravitational force is kind of the basis of what goes up must come down, because it is because of that gravitational force pulling everything back down to the earth. And we have a particular application for that, and we're going to talk about that now. Mass or weight. You'd see this in any sort of basic physics text or conversation when you're now getting into it. We know in our first video we talked about how what we call weight is actually mass. So now we're going to learn about what weight actually is. So I just said we know what goes up must come down, and that is because of gravity. That is due to the gravitational force pulling towards the earth. Now, this force of gravity on an object is what manifests as the weight of the object. Now, this is not to get confused with mass. Remember, mass is the amount of matter in a body, and weight is the force of gravity on a body. So how do we calculate this weight? Weight is calculated by saying the product of mass times acceleration due to gravity, or sometimes we see that as gravitational field strength, but we use those two terms interchangeably. So I'm just going to write that here, or acceleration due to gravity. So weight is equal to mass by acceleration due to gravity. So what exactly is acceleration due to gravity, or gravitational field strength? Now, if you think about it, if you're running, riding, swimming, or driving, you can accelerate. You can continue going at the same speed that you were going at, or you can accelerate. Now, the same thing happens when something is moving towards the surface of the earth or to the surface of some large mass. It will be falling, but it will accelerate to a certain extent. Now, the thing is that it's not like how we can control how much we choose to accelerate. This is going to accelerate to the same value every time. Now, this value that an object falling towards the earth with will accelerate with is what we call acceleration due to gravity. Now, on earth, we at this level take that value to be 10 newtons per kilogram, or sometimes you may see 10 meters per second squared. So you may see this, and they mean exactly the same thing. Now, the value is actually closer to 9.81, but for most CSEC exams, or most CSEC examination questions, I should say, we usually use 10. But don't just take it for granted and use 10, because they'll usually tell you in the question. If not in the particular part that you're doing, at the end of that particular question, they'll say use G as 10 newtons per kilogram or whatever. And on the moon, there's a smaller acceleration due to gravity, which makes sense if we think about it, because if you've ever seen astronauts on the moon, you see them kind of hopping around. There isn't gravity pulling them down. They have a little bit of, all I can think about is lightweightness, but you all know what I mean. I just can't think of the word right now. So there's a much smaller value of acceleration due to gravity, or for acceleration due to gravity on the moon, and the value we take for that is 1.6. Now, we do not have to remember this value for on the moon. Now, if we saw the formula for calculating weight, what is the unit? Now, weight is a force, and forces are measured in newtons and are represented by a capital N. 1 newton is the same as 1 kilogram meter per second squared. But how did we arrive at this? Let's think about the formula again. It says weight is equal to mass by acceleration due to gravity. Now, mass, the SI unit is kilograms, and G can be measured in meters per second squared. And this sentence here just told us that this is equivalent to 1 newton. But let's also look at it with the other unit for acceleration due to gravity. Now, weight is equal to mass by acceleration due to gravity. Mass is in kilograms, and acceleration due to gravity can also be measured in newtons per kilograms. Now, we're used to working with fractions, so we know that this kilogram could cancel with this kilogram, and then we'll be left with newtons. So you see, even if you forget what the unit is, which I'm hoping that we won't, it is still possible to sort of derive that unit. So let's look at an example. It says Raul has a mass of 60 kilograms. Determine his weight. Now, I have been delinquent and I did not put to take G as 10 newtons per kilogram, so I'm writing it in now. So let's try and figure this out. But before we go to work anything out, let's see what information they're giving us. It says Raul has a mass of 60 kilograms, so I'm going to highlight that. And they're asking us to calculate his weight. Now I'm going to write here, mass is equal to 60 kilograms. G is equal to 10 newtons per kilogram. And we're trying to find W. Now, we know the formula. The formula is weight is equal to mass by acceleration due to gravity. Now, mass is already in SI units, so we're good to go. We don't have to convert anything. So, mass is 60 kilograms, and acceleration due to gravity is 10 newtons per kilogram. And that would give me 600 newtons. And it's that simple. Now, let's try a question where we have to rearrange a bit. It says, the weight of an object was found to be 200 newtons. What is its mass? So let's see what information we're getting from this now. The weight is 200 newtons. Now we know what G is, and they want us to calculate its mass. So let's write down what information we have. All that we have so far is weight is equal to 200 newtons and G is equal to 10 newtons per kilogram. So I can write my formula. Weight is equal to M by G. Mass is, we don't know. That's what we're trying to find. But weight is 200 newtons. And then we have M for mass and G is 10. Now, in order to find for M, I have to get M on one side by itself. So whether you choose to think of this as carrying that 10 over to the other side, or whether you choose to think of it as dividing by 10, then we can get rid of it from on this side. And then what we'll end up with is mass is equal to 20 kilograms. And that is our answer. In the same way, if they said, hey, we're on some different planet. This is my weight, this is my mass. Find what the acceleration due to gravity on this planet is. We can do that as well. And I think that is what question 3 is about. So you can pause this, try questions 3 and 4, and see how you feel about that. But calculating mass is really that simple. Well, not just mass, weight and acceleration due to gravity. Now, we've just talked about weight and how weight is the effect of gravity pulling your body towards the earth. But we may think that our weight would act all through our bodies, but this actually isn't the case. Our weight seems to act through one point. Now, this point is called the center of gravity. So the center of gravity of a body is the point through which its entire weight acts. So if you think about it, my arm will be lighter than my head, and both of them are still lighter than my entire body. So if you hold up my hand, you won't feel my entire weight. Like let's say my mass is 55 kilograms. So I know if I multiply this 55 by 10, my weight will be 550 newtons. Now, if you lift my hands, so I'm standing and you just lift my hands, you're not lifting 550 newtons. You might be holding 100 newtons, I don't know. But you aren't lifting the entire weight unless you lift below or at the center of gravity. Now, something that is uniform like a ruler, the center of gravity would act in the middle of it because it's completely uniform. Its weight will be acting through one sensible point in the middle of the ruler. But something like our bodies that we know are a bit bigger in the midsection to lower down and smaller by our shoulders, depending on how you are shaped, that's your business. But our bodies aren't completely uniform, so we can't just say our weight will be acting through the center of our bodies. Most of us, our weight would act through somewhere around our mid-center, so that's where our center of gravity is. So we see here now, we're seeing an A, center of gravity here. Even if you kind of stick your hip out and stand kind of at an angle, your center of gravity stays the same place. Even if you lean over to the side, your center of gravity remains the same place. You could be upside down, your center of gravity would still be acting through that same point. So that was an example of how it is for a person. But for different objects, we'll see here that the center of gravity would usually be closer to wherever most of the mass is on whatever is the object. So one of the things that we often think about when we talk about center of gravity is how or what this has to do with stability. Now, one thing we always have to keep in mind with stability is that an object will topple over if its center of gravity passes outside its base. So this is your base here, your bottom, the base of this particular bus, and this is where the center of gravity is. The weight will always continue to act downwards. Even if he tilts, or the maxi tilts rather, why am I saying maxi? Is a bus here, but you all know what I mean, maxi bus, whatever. Even if it tilts, the weight will still continue to act downwards. And if it tilts so much that the center of gravity is now acting outside of this base, this will topple over. Here we see two of the factors that affect stability. Now, in the first picture, we have two cars. One has a pretty narrow base and one has a wider base. Now, because of the width to height ratio, what will happen is that it's much easier for this car for its weight to end up outside of its base and for it to topple over. But this car, because of how wide it is, it will have to tilt so much more for its center of gravity to be outside of its base for it to topple over. And also, look at the height of the center of gravity. With this car, the center of gravity is higher, and with this car, the center of gravity is lower. And this is another thing that affects stability. The higher the center of gravity, the less stable this is, and the more likely it is that the center of gravity will end up passing outside of its base, and whatever the object is will topple over. Now, this is why those race cars, whether it's NASCAR, whatever, I don't really know anything about that, so I don't even know what the correct name is, but these cars are always very low to the ground and have a pretty wide base, like when you think about go-karts. And this is so that when it's going at this ridiculously high speeds, it is much less likely to tilt and topple over. Because it's close to the ground, it's pretty hard for the center of gravity to end up being outside of its base. And it's the same way when you think about wrestlers, like real wrestlers, when they're going to fight, they always sort of squat down. They're squatting down so that, one, they're going to spread their legs, which means they'd have a wider base. So it's harder for them to topple over, and they're going down, so the height of their center of gravity will now be shorter, so it's more difficult for them to topple over. So you see, these are all applications of weight and center of gravity, but we just don't really realize how it works. And on the note of center of gravity, this is how people are able to do cool things like making these things balance, because whether they even know about center of gravity or not, that's what they're using here. Because once the center of gravities are aligned or stacked one above the other, then this will remain balanced like this, and the apple and fork and stuff will not topple over. So you could go and check out those videos and see how cool and mind-blowing it is that these people are able to do that. So that's it for today, guys. I hope this helped you all understand how forces work and weight and center of gravity. And why am I feeling like I'm forgetting what I'm saying? I'll see you guys in the next video. Thanks again, and remember to stay safe and be kind to yourselves, guys. Bye bye.